In this section, we're going to discuss cycloalkane stability, and we're going to look at cycloalkanes from C3 up to C6 and look at some of the different trends in their stabilities. As we talk about this, one thing that I want you to keep in mind the entire time is that the most stable alkanes have a 109.5 degree bond angle and a staggered conformation. So that's because the cycloalkanes, or alkanes in general, have sp3 carbons with 109.5 degree bond angles. That's ideal. And being in a staggered conformation, where all of the atoms are staggered, not eclipsed, is going to be ideal. So with that in mind, let's start with cyclopropane. So here we have the structure of cyclopropane. It's a 3-carbon ring. And I have up this online model kit, which the link is going to be with your lecture notes for today. So you can either build a molecular model if you have a model set, or if you want to use this ChemMagick virtual model set, you can do that as well. Here we have the cyclopropane structure, and you can see that it is this small 3-membered ring, just rotated around in space so you can take a look at it. And one of the first things that you should note is that the bond angle is very, very small here. The bond angle is 60 degrees. That's important because that's quite a deviation from 109.5 degrees. So we can say that cyclopropane has significant angle strain. And when we talk about angle strain, that means deviation from the ideal bond angle. The next thing that I want you to look at really has to do with the 3D structure and conformations. So if you think back to what we did with Newman projections and drawing cycloalkane conformations, think about looking at one of the carbons on this ring from the end. So I'm going to rotate this so that we're staring down this carbon right here. So the bond you're staring down is this carbon-carbon bond. And as we stare down that, you can see that the hydrogens are all eclipsed. They line directly up in front of one another. They're perfectly eclipsed. So what that means is there's significant strain resulting from that eclipse, and we call that torsional strain. And torsional strain is a result of eclipsing atoms separated by 3 bonds. And that's exactly what we have here. If you're looking at what's eclipsing, we're going to have a hydrogen, carbon, carbon, hydrogen. Well, how many bonds are between those? 1 bond, 2 bonds, 3 bonds. So what we can actually do with this is put this in the form of a Newman projection. And here's our front carbon. Here's our back carbon. So now if you draw the Newman projection, back carbon, front carbon, and the back carbon, I'll draw in a hydrogen, and then you have this CH2 that's part of the ring. And then on the front carbon, we actually have just eclipsing. So we have this first hydrogen, which represents this hydrogen here. We're going to have our second hydrogen, which represents this hydrogen right here. And then this front carbon is connected to the carbon of the ring. So it's a little hard to see exactly, but we'll connect it right there. So that's how we kind of draw this Newman projection of the cyclopropane. And again, you can see that we have these eclipses. Just to show you one other way to draw this, I'm just going to draw on a couple of the hydrogens. This is kind of a slightly 3D way to draw it. And mainly this is just to point out, for example, these two hydrogen are eclipsing. These two hydrogen are eclipsing on the bottom. And to show you the bond separation, 1, 2, 3 bonds between the eclipsing hydrogen. Same way down here on the bottom, 1, 2, 3 bonds separate them. Because of the nature of putting 3 things together, these 3 points are going to give us a completely planar structure. So at least the 3 carbons in the ring are in the same plane. And the relative energy of this particular conformation, this isn't a number you need to memorize, but we'll use it to compare the other cycloalkanes. It's 9.2 kilocalories per mole. Now we're looking at cyclobutane. It's a 4-carbon ring. And one of the first things you should spot is that these bond angles appear to be 90 degrees. We'll see they're not exactly 90, but here is the 3D structure of cyclobutane. And if you look at this, what we find is that unlike cyclopropane, if we move this around just a bit, we'll find it's not completely flat. The carbons in this ring aren't completely flat. In fact, they are bent or slightly folded. So we call this a folded structure. Also, if you look along any of the carbon-carbon bonds, you'll see that the hydrogen aren't completely eclipsed. They're not completely staggered either. They're somewhere in the middle. But what this folding does is it relieves some of that eclipsing, because if you flatten this structure out completely, that would move these hydrogen such that they were eclipsing the others. So this folding changes the bond angle a little bit. So instead of being 90 degrees, because it's folded, that does constrict the bond angle just a bit. So the bond angle for this is 88 degrees. And we say that it's a slightly folded structure. And that is to relieve torsional strain. So we'll save a couple of viewpoints here just to help visualize this. So here you can see the slightly folded structure. You can see that this isn't completely eclipsed, but it's somewhere between staggered and eclipsed. So it's not strain-free like a staggered conformation, but it's also not nearly as bad as a fully eclipsed conformation. So it's kind of somewhere in the middle. But it does have significant angle strain. And because of that, it still has a relatively high energy. The relative energy is 6.6. So it's lower in energy than cyclopropane, but it's still fairly high in energy. Next, we'll look at cyclopentane. So it's close to ideal, but it's not, doesn't have the exact 109.5 degree bond angle. It's 108 degrees. And if we look at the 3D structure of cyclopentane, we have this structure here. So as you can see, cyclopentane is not completely flat. And in fact, it's a little difficult to get a good viewpoint, but you can see that any of the given carbons, if you have these kind of in somewhat of a plane, this one is bended up slightly, And this is often termed an envelope shape. So you can see you have like the bottom of the envelope and then the flap pointed up. So I'll write that out for you in a second. The other thing I want to show you here has to do with the conformation. So let's say we view along the two carbons here. If I arrange this such that you're looking along the two carbons, you can see that they're almost perfectly staggered. Not quite, there's a slight skewing, but the atoms are almost perfectly staggered. So there's very, very little torsional strain. Right, so in this first one, we see the envelope shape. And again, we kind of have the bottom of our envelope, and then this carbon makes the flap of the envelope. From our other viewpoint here, if we're viewing along, we have a front carbon, and then you can't really see it, but there's a back carbon back here. You can see that the hydrogens on each carbon are nearly staggered. So that means this molecule has very little torsional strain. And because of the bond angle, 108 degrees is almost ideal, so it has very little angle strain. There's not much strain at all in cyclopentane, just tiny bit of torsional strain, a tiny bit of angle strain. So the relative energy is rather low. The relative energy is 1.3 kcals per mole.
Now we're going to look at cyclohexane. And let me start by saying it's pretty much the gold standard. Its relative energy is 0. So it's what sets the base for what all the other cycloalkanes are calculated off of. So cyclohexane is the most stable cycloalkane. Let's take a look at the model of cyclohexane. And what we can see if we turn this on its side is that cyclohexane is not flat. Okay, you can see that the carbons in the ring are not in a single plane. Instead, what we have in cyclohexane is what's known as a chair conformation or a chair structure. And if you look, you have to get it at just the right angle, but you can see how these carbons sort of represent a chair. You can think of the foot of the chair, the seat of the chair, and the back of the chair. In terms of the bond angles, cyclohexane has a perfect 109.5 degree bond angle, and that's the case for all of the carbons. And then if we want to look at torsional strain, we're looking to see if the hydrogens on the carbons are staggered or eclipsed. Well, if we look at this, and if I line two carbons up in front of one another, hopefully you can see that we have this perfectly staggered structure where the hydrogens on the front carbon are staggered with the hydrogens on the back carbon. So again, here is the chair structure, and we'll learn to draw this in just a bit, but you can see that we have our carbons of the chair like that. And then if we look along a carbon-carbon bond, we have, here's our front carbon. Behind that, it's hard to see, but you have a back carbon. And then on the back carbon, we have the hydrogen, hydrogen, and the ring. On the front carbon, hydrogen, hydrogen, and the ring. And that is completely staggered. So there is no torsional strain. And because of the perfect bond angles in the chair form, there's no angle strain. So that's why it's our most stable cycloalkane with a relative energy of 0.